Hello, welcome to the new session number 18 in the series Microwave and Millimeter Wave Circuit Design. My name is Anurag Nigam, and today in this session, I'm going to talk about gain stages. And I'll do a small signal matching and show you how to do that. And I will also tell you, what things are important when you do the matching, right? So what I'm going to do is I'm going to create a new schematic, right? And I will call this a schematic. So I'm going to use a process which is kind of old now, which is almost like a 15-year-old process. It's a zero point 0.5 micron process, but this goes up to like 33 gigahertz, right, cutoff frequency, and it has got both depletion and enhancement mode devices. So I'm going to use a enhancement mode device, right? So what people do is when they see a transistor like this, right? Okay, first they are bothered about what is the sizing. Now we will talk about sizing later on. But for now, let me just show you a small matching exercise, right? So let's say that this is each finger is 70 micron, and there are 24 such fingers, right? And next thing is over here, there are some things which I will make sense later on, but I'm going to set something like merge context, which I'll talk later, right? Okay, so now this is the device. Now, the first thing people do is they put here a ground. This is wrong. Why this is wrong is because this is a source which is grounded, which basically decides the input as well as the output impedance. Now this is a perfect ground, while in realistic design this is not going to be a perfect ground, right? So now what this ground would be, okay, so if I was to, let me just save this. Okay, so let's say this I call as a driver stage. Okay, so I save this as a driver stage. Now let's make a new schematic or new layout, for example, right? And in this layout, I'm going to put in a device, right? The same device which I have put there. And I want to show you, okay, uh, what this is all about, right? So let me, option preferences, let me see, read layout. Okay, fine. So I just adjusted the grid. Okay, so if you go to go to options, preferences, grid snap. So I'm working on a 0.01 recommended grid for this process. Okay, that's fine. So I'm going to take an enhancement mode device. This is a 70 micron finger, and there are 24 such fingers, gate fingers, and then the contacts are merged. Okay, and say okay. So the device basically looks like this, right? And you see that the device doesn't have so it has got the drain terminal, the gate terminal, and the blue one which you see, the metal 2, is going to be the source terminal. So the way they have modeled this device, if you see there are 3 terminals, right? So they must have done the probing, right? They must have done the GSG probing. That means that the ground via is not a part of the model, right? So the grounding is not part of the model. So if grounding is not part of the model and you directly put here a ground, okay, that's difficult to create. That's impossible to create a perfect ground here, right? So the device basically is going to see vias, right? So if I was to put here substrate via, now some processes may give you two models, one with the via, one without the via. In that case, you do not worry. You can use the one with the via. But again, you should know how they probe the device for modeling. In this case, they have probed it like a GSG on input and output, and the ground was basically the emitter on both the input output side, right? So that's how they probe the device. Now what I'm going to do is, if I put these two vias, I must know what is the ground inductance. And that inductance I'm supposed to put here, and that way my input and output impedances would be meaningful. If I directly put here a ground and then do the matching, then I have just wasted my time, because in practice, perfect ground will not be there, right? So the key in a common source design for your gain stage is to figure out what is the inductance over here in the ground, and that basically means that you have to put here this via. So let me just put this via, and then there are certain DRC rules, right? and so you have to have the spacings as per the DRC rule. Let me just switch off some of the layers. Okay, now this is moved. So I move the center over here. Now can I leave this like this? Answer is no, right? I have to have, because there are certain metal to metal spacings which come into figure, right? So you cannot just do that, right? So I'm going to move this relative, and I'm going to move this by, let's say, -20. Okay, and then sorry, and then on the other side I am going to do the same thing with this one. I am going to move this. I'm going to first align the center and say edit, move, relative, and go out by 20 micron, let's say. Okay, so this basically is my ground configuration. Now, if I change the ground configuration, the inductance over here will change, and that means that the input output match are going to change. So that's how the layout is linked with the schematic, or the layout is linked with your matching, right? So you should basically think in advance what you're doing. So let's say I'm going to say this lay DRV. Okay, save. Now I am going to use metal 2. Okay, so first of all, let me show you the substrate. Okay, now okay, uh, yeah, the substrate basically has got, okay, 3 metal layers, right? And metal 2 is basically uh, where your ground is, right? Substrate, just 1 second, momentum, substrate, open. Yes, is there a substrate which I have? No. Okay, uh before this, okay, so let's say metal 2 is there, right? I'm going to make these changes to the substrate, so I will use metal 2. So this is metal 2, and I am going to connect metal 2 over here like this, and okay, okay, and the same piece is going to repeat on the other side, right? And that's how it is done. So sorry, I should copy this portion. Okay, and then I will also create a piece over here like this, and a piece over here like this. Okay, so now I can remove the device. Okay, it didn't work. Metal to me. I want to put one piece over here like this, and another piece over here like this, and then I'm going to delete the device. Okay, so then the configuration looks like this, and then there is a ground plane, and you are supposed to know the inductance to the ground, right? So I have already simulated that, so let me just show you that somehow. Okay, let me just look at create modify substrate, create modify. Okay, so here is the modified version, and why I'm not able to save it. Eh, okay, this I'll figure out later on, right? Okay, so now there has to be a way to save this, right? Okay, this is an older version of ADS, right? But anyways, so I'll figure it out. So now you see that there are layers which come up to the bottom layer, which is a conductor. So this is the layer on the board, right? And if I look at the 3D of this, so if I go to EM preview of this, Okay, so basically the device sits here. Okay, so the device is sitting here, right? And then these substrate vias go all the way through back to the board, and this brown thing is the metal layer on the board, right? And these are the substrate vias, and the ground is established uh, by this vias, which has an inductive ground. So if what you have to do is, first of all, you have to find out what is the inductance. So you have to EM simulate this. Now you should EM simulate with a DC point in it, because all the current will go through this. So your simulation will be from DC to the frequency where you are designing almost the fourth harmonic of it. So for example, let's say I'm designing at 5.8 to 7.2. So 7.2 into 3, at least third harmonic or fourth harmonic should be there, right? So let's say if I am doing 7.2, so 40 gigahertz is a frequency up to which I will characterize this, right? Now the thing is that whichever is minimum, 40 gigahertz, or if the process is only up to 33 gigahertz, let's say, so 33 gigahertz is the right frequency up to which I want to characterize this, right? So that harmonic terminations are correct. So that's why I'm going to do up to third harmonic, and these odd harmonics are important in case of a PA, right? So we will talk about this later on. So this is there. Now once you do this simulation, okay, you can generate a lookalike component for this, and then what you do here is you create your schematic, and you say file save design, and you save this design as uh, matching DRV, for example. So I'm going to do a driver stage matching. Okay, so now the question is, so I have got two schematics here. Okay, so one is over here. Here I will do the DC. Okay, so let me bring that component over here. Okay, so this is a lookalike component for that, right? So it looks alike the layout. So you can generate a lookalike. So this is going to establish the ground. This is going to be the inductive ground. And what does it look like? So let's just see what does it look like. So if I take a S parameter, simulation, so if I go to find out the simulation S parameter. So let's see what this looks like up to 40 gigahertz. So I'm going to go from DC. So this is already simulated, right? So to save your time, I simulated this, and let's say I'm going to do 1 megahertz. So this is an adaptive model, so it is going to interpolate or whatever. And then I'm going to look at, let's say, terminal, and I'm going to look at the single port simulation, right? So I'm going to just look at what kind of inductance I'm seeing at the ground. Oh, too many frequency points. Well, anyways, so I shouldn't take that many frequency points. 10 megahertz, 100 megahertz is good enough. So let's do this again. Okay, there you have it. So if I put here S11, so it looks like an inductive ground. You can see this. Okay. Okay, so it looks like inductive ground. So let's say if I'm designing at let's say 5 or 6 gigahertz, right? So it is going to look like J 1.28, right? So this is an inductive ground. Okay, and this is what I have done, right? Now I have to find out what is that inductance value, right? So what I can do is I can write here an equation. I can say ZS. So I'm going to convert S parameter to Z parameters, right? S to Z, and then I can say S, right? So that establishes the Z parameter, and then I will find out the inductance value because there is only Z12. So I can say LSH is equal to imaginary of Z S divided by 2 pi frequency, 2 into pi into frequency. Okay, so that is going to be the shunt inductance. Let's plot that shunt inductance. Okay, equation shunt inductance. So that shunt inductance is 34 picohenry. Okay, so your ground, which this transistor is saying, is 34 picohenry. It is not a perfect ground, right? So now let's do the DC simulation. Okay, so this I have enabled, and I'm not going to do S parameter. I'm going to do DC simulation. So I am going to put here again. Okay, I'm going to put here two inductors. Now people will put here what is called a choke or a DC feed, but I'm not doing that for a reason, because if the transistor is oscillating, my DC currents are wrong. But if I put an inductor with a loss, then it might be stable. More chances of this being stable. So rather being inaccurate is better than being totally absurd, right? So I am going to put here lump components, and I am going to put here, let's say, 5 nanohenry with the 3 ohm resistance. Okay, so I'm going to put here 5 nanohenry with the 3 ohm resistance, right? And then I'm going to use the same thing on the other side for the gate, right? So this is done, and then I'm going to use a bypass gap, right? So let's say I'm going to use all ideal components for now, right? Other than this via, which was important. This I'll put as, let's say, 4, and I'm going to repeat that on the other side. Oh, this is a problem of this version of ADS. Okay, and then I'm going to take two sources, DC sources frequency domain. Okay, one is VDS, other is VGS. So this is going to be VGS, and this is going to be VDS. Correct. And if you are using variables, then you have to better declare them, and that you are going to use using a var parameter. So you are going to use a var, and then you are going to declare a VGS, and this is case sensitive, let it be 1, and then you are going to do VDS. This is also case sensitive. So that's done. And then I am going to put two capacitors here. So I am using these components for a reason. I could have used a DC block, but then, if the transistor is unstable, then the DC characteristics are wrong. So I'm going to rather put here 2 picofarad here and 2 picofarad here. I'm anyways doing a DC, but I'm providing a RF termination to 50. And I'll tell you why once we do the S parameter on this. And I'll terminate this to 50 ohms. So S1 and S2. Okay, so now I have this, and I should measure the current here. So I will put a probe component. So component probe, and I have to flip this, isn't it? Yeah, so that the direction of the probe is same as the arrow, and this I will call as IDS. Okay, so I'm measuring the current IDS for different values of VGS and VDS. So now I'm going to do DC simulation. So go to simulation DC, and here I am going to put here VDS, and VDS I'm going to go from 0 to, let's say, 5 volts in steps of, let's say, 0.01. Okay, and then in the display I'm going to display start, stop, step, and variable. Say OK. So I'm sweeping VDS from 0 to 5 volts. Then I'm going to do a parametric sweep for VGS, and here I'm going to sweep VGS, and I'm going to go from 0.2. So the pinch off voltage for this one is 0.35. So the device is going to turn out at 0.35, 0.45 in steps of 0.01, let's say. Okay, and the inner loop is in DC1, and we are all set. So once this is done, I am going to put a include file in this. Okay, so I'll go and put a include file for the device. Okay, so now that we are done, we are ready for the DC simulation, right? So again, why it's not showing this step here? Because of this. Okay, so now I am going to just do a DC simulation on this. And establish a quiescent current. Later on, I will come and tell you what are the difference. Okay, so don't worry about. Okay, this is from somewhere. I'm gonna just delete this. Oh, this is from the previous one, right? We were finding out the inductance. Now here I'm going to plot IDS. Okay, so this is the characteristics of the device, and let me put a label on this. Okay, so I am going to bias this at 3.5 volt as VDD. So if I put a marker, my quiescent would be around my quiescent current would be around 22 milliamps, right? And operating from 3.5 volts as drain voltage and 0.45 as the gate voltage, right? So I'm going to put 0.45 as the gate voltage. Okay, so this one is 3.5 and this one is 0.45, right? So this will establish a 22 milliamps of current through this device, right? So now we are done with the DC simulation. I'm going to just take this part of the circuit and I'm going to do a S parameter on this. Control C, cancel this, save. Okay, so here in this schematic I am going to do that. Okay, so I'll do a control V. Okay, so now we have the device and now I have to do S parameter simulation on this. So I'll go to simulation S parameter and I am going to simulate from our in band, which is 5.8 gigahertz 5.8 gigahertz to, let's say, 7.2 gigahertz 7.2 gigahertz. Okay, and steps of, let's say, 10 megahertz. Okay, so now we are doing S parameter simulation on this. Now first thing is the device has to be stable. Now if the device is not stable, your matching will make no sense, right? So let's see what is the stability of the device. So you go to source stability circles and load stability circles, right? So once you put these two over there and simulate in your band, you're just going to say simulate. So this is biased. You can look at simulate annotate DC. Okay, so it is drawing 21 milliamps of current roughly, right, at 0.45 volts, right? So simulate, clear annotation. Okay, so now this is biased correctly, right? And it has given you S parameters. So let's look at S11, okay, and S22. And the good part is they are inside the Smith chart. So if the device is unstable, most likely they are outside the Smith chart. But let's look at the load and source stability circles, and I'll explain you what those are in a bit. Okay, before I do that, I will move the auto scale out. So now you see that these circles are over here. Okay, so what does a load and source stability circle mean, right? It means that these are reflection coefficients gamma in and gamma out for the values of 1. So what does it mean for a device? So let's look at a device. So maybe I can cancel this one. Okay, so for a device, gamma in is looking into the input and gamma out is looking into the output. Now if I put energy into the input and the same energy reflects back, exactly same amount, then the gamma is 1. Similarly, in the output, if I put some energy and same energy goes out, the gamma is 1. And gamma is 1 is a borderline. If gamma is more than 1, That means you are getting more energy out of it than you are putting in. What it means is that this device is a source of oscillations at that frequency, right? So if your gamma is more than 1 on input and output, then the device is oscillating, and the borderline is gamma in equal to 1 and gamma out equal to 1. So all those impedances for which gamma in and gamma out are equal to 1 are these circles, right? Now if you look at these circles, so if I consider this circle, then there is a portion of Smith chart which is enclosed by this circle, right? And similarly there is a portion of Smith chart enclosed by this circle. Now how would I know that whether this part is gamma greater than 1 or that part is greater than 1, okay, which is the outside part? Okay, so to establish that, I'm looking at magnitude of S11, and the magnitude of S11 is less than 1 because it is inside the Smith chart, right? So the magnitude is less than S11. Magnitude is less than 1. So that means that the entire region over here is stable. And if you go inside this circle, that portion of the Smith chart inside the circle is unstable because the gamma is more than 1 and the borderline is gamma equal to 1. So these pink circles which you see here, gamma equal to 1. So the right side, which is the entire Smith chart, is gamma less than 1. And what is inside the circle is gamma greater than 1. So that means whatever is enclosed by this pink circle, that is an unstable portion. Any impedance in this region will cause oscillation. Similarly for this magenta, this color, right, turquoise color, these circles, whatever is outside, okay, which is the part of the Smith chart here outside of these circles, is gamma less than 1 because S11 and S22 magnitude is less than 1, and S11 and S22 magnitude is the center of the Smith chart. So right, so basically how do you establish stability? Using these stability circles, gamma in equal to 1 and gamma out equal to 1, and then you establish which part of the Smith chart is stable, the one which is enclosed or the one which is outside. So basically if S11 and S22 are in this region of the Smith chart and their magnitude is less than 1, then this portion of the Smith chart is stable, while the other portion which is enclosed by the circle is unstable. So that way 50 ohm is stable. So now you know when I did the DC parameters, why did I terminate them to 50? Because I want the 50 ohm as a stable point. So if 50 ohm is a stable point, then my DC characteristics are correct. So usually what people do is they directly put there. So they don't put here decoupling. They directly put this DC voltage source to the gate and the drain. That is wrong because then you are showing this transistor a short. Okay, so you are showing this transistor this short, right? And if you show the short and let's say by chance these circles are over here, then this is an unstable portion and your DC characteristics would be wrong, right? So the best bet is the point farthest away from the boundary. So the point farthest away from the boundary of the Smith chart is the center. So that's why I terminated into 50. So that's whole of the point of putting this decoupling for the DC decoupling and then putting a RF termination of 50 ohm. So you understood why we did a DC characterization with the termination into 50 ohm. Okay, and then these stability circles are far away, so I don't care. I will directly proceed with the matching part, right? So this inductor can be part of matching, but if you make the inductor to be part of matching, okay, then you have to create a very good short here, RF short, which means that these capacitors have to be low ESR and they have to be large values, right? Otherwise you can put here a tank circuit or a quarter wave line for decoupling. If you want to use this as a part of tuning, right, then you have to have a very good RF short here, because otherwise the internal resistance of these batteries which you use in the physical world is going to affect your matching. So you have to create a very good short at these 2 points. Okay, so you can use this you can make the short using a radial stub or an open circuit stub, right? That is the best short. Or if you use a capacitor, then its ESR should be very low, effective series resistance. Okay, so now enough of chat. Let's go ahead and try to tune it. So we know I am going to put another Smith chart on it, both. Okay, so we know I need to move this way. So I will move this blue one, which is S22, this way, and the red one I'll move that way and that way. Okay, so I will use a series inductor here and a shunt capacitor, right? And in this case I am going to just reduce the series inductor. Okay, so let's see. Let's put a tune on this one. Tune, and I'm going to put a tune on this one and a tune on this one, right? So let's see how this affects. So if I reduce this value, okay, so they are kind of going far away. So this is not what I want to do. This is counterintuitive. So I'll keep this around, let's say 3.5 is the 3.3 or 3 ohm, 3 nanohenry, for example. That's good enough. And let's say this one is bringing it closer. So let's say this is 1. Oh, sorry. So this is 1. And if I bring this down, nothing is happening. Right, so let's leave this here close, and I am going to put here a series inductance. Okay, so I'm going to work with the ideal ones first. Okay, some things which I can replace. I can replace this with the SVR. Okay, so if I go to TQPED, there is something called SVR, so some inductance is over here. Okay, so now I am going to put here an inductor. Okay, I'm going to take the same inductor and rotate it out and put it over here. And for this value of inductor, 2 ohm is good enough. Roughly, when you do EM simulation on inductors, you will come to know that. And similarly here, roughly 2 ohms. Later on, we will establish this. Right, so this will throw this over here. So let's start with 1 nanohenry. Okay, and then for this one, I am going to use a shunt inductor. So a shunt inductor will move this to that way. So I'm going to use a shunt inductor over here. So I'm going to just copy this one over here. Again, I'm going to use the ideal for now. Later I'll put the vias. Okay, so now let's simulate that. Okay, so this has moved up to here and this has moved up to here. Now this has to come down, right? So let's go ahead and do the tune again. So now we are talking about L4 and we are talking about L3. Okay, so I have gone a way up, so L3 has to be smaller. So let's say 0.5. Okay, so L3 has to be smaller. Okay, so L3 is over here, for example. Let's say this is the mid frequency. Sorry. Yeah, roughly here. And then this is basically the output side is L4. L4 has to be reduced to move this up. L4 has to be reduced. So again, I will put this as 0.5. Okay, and L4 is being reduced. But again, this has to be pushed the other way, right? So this is basically this capacitor, right? So this capacitor, if I reduce, it will push it out. Okay, so now one of them is matched. Okay, so one of them is matched. Okay, so now I'm going to update this and close it. So S22 is matched. S11 is over here, so I need a capacitor here, right? So I'm going to put here a capacitor. So I'm going to go here to lump components and pick up a capacitor. Okay, and let me just, okay, and this capacitor value, let's start with 0.5, small capacitor value, and I am going to put a tune on this again. So on this capacitor I'm going to put a tune, and let's look at what happened to the match. So this capacitor needs to be increased. So if I increase this, so let's say this is going to be equal to, let's say 2. Okay, so let's say this is aligned like this, and the capacitor I can increase to bring it back. Okay, so now you see that the match is okay, but this match is going to be very narrow band, isn't it? Because it is matched for a frequency, it is matched. So for a frequency it is matched. So for this frequency over here, whatever that frequency is, okay, so that frequency is around 6.5 gigahertz. We are close to 50. Okay, similarly on the output, we are close to 50. But then you see the excursion is a lot. That means that this match is a narrow band match. You can see this in a rectangular plot also. If you look at S11, okay, and you look at S22, okay, and you will see that S22 is better than 10, but S11, because the excursion is very large, S11 is really bad. Okay, so now there is a trick. Okay, you just don't struggle. Okay, I have already shown you the trick of doing broadband match. So what I'm going to do is, let's say that this is my final match. Okay, let me update this and close this. This is my final match. So basically I'm using this, right? So I'm going to copy this portion, Control C, and I'm going to make a new schematic. So I'm going to make a new schematic and call this as match. Save design as source match. Okay, and say Control V. So this is my source match. So I have transformed 50 into certain impedance. So let me see what that impedance is. So if I go to S parameter and go to terminal, right, I want to look at S22. That is my impedance. Okay, so I go to S parameter and I look at my frequency of interest, which is 5.8 to 7.2 gigahertz, correct? And I will put here megahertz, 10 megahertz. Okay, so if I do the simulation here, okay, and look at S22, okay, so my match is over here. So let's look at the center frequency. Okay, marker new. Okay, so the center frequency is, let's say, 6.5 or 6.55, right, roughly, and let's say normalize to 50. So I'm looking at 8.43 J 3.2, and I need to match the conjugate of that to 50, because the transistor is conjugate of what I'm seeing here, right? So to do the matching, I'll just repeat this terminal. Okay, and over here I am going to write the impedance to be 8.43 plus j into, or in this case minus j, because it is a conjugate, right? Minus j into 3.214, correct? Okay, and I will put ohms here. So this is the transistor input impedance, which I have to transform to 50 ohm. Okay, so let's look at this like this, and then you use your matching skills, which I have taught in the previous session. So if I do this, and if I look at S44, that is your transistor match over here, and I'm supposed to match. So let's put here admittance chart also, both. Okay, so I'm supposed to match this point to 50 without a lot of spread. So what I'll do is I will use a capacitor to go down, then I will use a inductor to go up, and then I will use a series inductor to go this way and then come back this way. Okay, so that is what I have told you in broadband matching, right? So I'm going to use this one over here. Okay, and I will say tune, and here I have to don't touch L3 because L3 is a part of, or C3, I have to work up with C6. Okay, so that one I don't have to work with. C6 I have to work with, right? So I have moved all the way up to 50 ohm. I don't want to do that, right? So I have moved all the way up to 50 ohm. I don't want to do that, right? So basically that capacitor has to be increased. Okay, somewhere here. And say update schematic close. Okay, so that capacitor is established. Now I'm going to use inductor to go that way. So I'm going to take this inductor and rotate it out. Rotate and place it over here. So the inductor is going to take me up. So again I'm going to go to tune, and that inductor is L4, right? So L4, if I reduce L4, it's going to take me up like that, right? So update schematic close, and then I need a series inductor. So let me first disable these guys because really they are creating a nonsense here. Okay, that's gone, and that's the tune which is gone. Okay, so now I have to put here an inductor. Okay, so this inductor here will copy here. Now the idea is to make a match which is the least spread match, isn't it? So I'm going to again go to the tune, and here I am going to tune this inductance. Okay, so I am going to come to 50 ohm here, right, with the help of this inductance. Okay, so this inductance, this is L5, right? So if I increase this, I am over here, and then I have to use a shunt capacitance to come down. So I am going to use a shunt capacitor to come down. So I'm going to use this capacitance. Okay, and I'm going to put a tune on C7. Okay, I'll put a tune on C7, and I'm using this capacitor to come down. Okay, so this is going to be 0.4. So now notice that the smallest excursion you can make, you see, the smallest excursion you can make is going to give you the best match. You understand what I'm saying, right? So this inductance has to be increased to go that way. Okay, so don't spend a lot of time. So roughly this is the excursion. So you look at the spread here and look at the spread there. So I'm going to update schematic and close. Now I'm going to replace that match with this match. So I'm going to say Control C, and I'm going to go here and throw out this match. I am not interested in this match, right? And an application engineer will tell you that you use a Smith chart utility. Yes, but then what you have learned here as an insight into this, you will not have that. So now I have tune on all this. L2 and L1 I'm not going to touch, and remaining I can touch. Okay, so I am going to put here a tune on this one, and this is not what we are looking at. We are looking at this one. So now you see already the spread is less, right? Okay, but then S11 is not better than 10, right? So let's go ahead and work with the tune. Okay, so C7. So when you move this, you will come to know what's happening, right? You see, this is moving away, this is moving closer. So if I put this as 2, this will come even closer, right? So you see here, we have come this way. So now this spread is less, right? Isn't it? So wait. Okay, now next is, you see, so this is your input. This is L1. I'm not supposed to touch this. I'll leave this at 3. Okay, so this is L2. I can touch L2 if I want. Okay, so this is L4. So this is L4 is your output side, and this is capacitor C4, which is again the input side. Okay, so the idea is to reduce the spread. Okay. Three 3.5. So this is your input match. So this you are not supposed to touch, right? And this is your output match. Sorry. L1, L2 I'm not supposed to touch. L4, C4 I'm not supposed to touch. L5, this is I'm supposed to touch. But then C, there is one more L which is missing, isn't it? Hang on. What is that? L6. Where is L6? Where is L6? L6 is over here. Right. Command. So you have to have a good mouse to have this control. Okay, so I'm going to stop here. Update schematic close. So now if you look at this one, you will see you have better than 10 dB match on both input and output, and your S21 is a gain which is close to let's put a marker 8.6 on the left side and 8.5 on the right side. So now I will just get this S22 down a little so that I'm balanced. Okay, I'm going to look at this one. S22 is L4 C4, L4 and C4. So I'm going to increase this a little, correct? And L4 and C4, L4, correct? And let's see if I can improve this one. Oh, it has gone worse on the other side. Okay. Somewhere here, Okay. Oh, okay. Another thing to worry about is the droop, right? So let's work with this one. Hang on. So this is 8.3 and this side is 8.2. So just one more shot I'll take at it. Right. Now, okay. Okay. So it is 8.6 on the left side and 8.34 on the right side, 8.6 and 8.4, and this is better than 10. So this is the match I would accept. Okay, so I have just told you. Okay, what did I tell you? Okay, I told you how to do a simultaneous match on both input and output. Okay, for a maximum gain. Okay, now is this match good for a PA? No. Is this match good for LNA? Maybe, because we don't know the noise figure, right? If you want, you can see the noise figure also, because if you were to tune this for a LNA, you would like to see the noise figure, right? So to see the noise figure, you just have to go here and noise and say calculate noise and say okay. And then what you have to do is you have to put here option, okay, the temperature, right? So if you go to S parameter simulation, there is an option and the temperature which you put here is going to be 16.85. Okay, and why 16.85? Because that is your IEEE standard, otherwise it is going to give you a warning. 16.85 Celsius. Okay, and just sit simulate. Okay, so if I look at the NF2 here, that is your noise figure, that's very bad. And NFmin, okay, that is 3.6, that's also bad. And you know why that is bad? That is bad because of the losses in these components which you have put here. A 0.6 nanohenry you try to create at 1.2 ohms, and similarly 0.29 you will create at 1 ohm, and then you hit simulate, then it has improved to 3.2 something, and the gain has gone up, right? That's okay. So you would have to retune it. Okay, so you can tune for the noise figure, but what is going to happen is if you change the source inductance, you improve the source degeneration, then the noise figure is going to improve, right? So for example, and the stability will also improve, but the gain will go down, right? So let me just, if my target is 1 point something, right, then these numbers are really bad. So let me just put a tune on this one. Right, and let's look at my matches, right? And I have to improve, I have to improve this number. Just 1 second. So this is 3.2. So I have to be better than 10, right? Okay. And look at your noise figure also, right? Keep an eye on that one. So if it is mismatched, of course the noise figure will go better. That's not the way to do it. And then the third thing is the quiescent current. But then you are not tuning this as a LNA, right? This is a PA is a different size. LNA is a different size, right? So you understand. So I have given you just the tools. Okay, I have just told you the tools. Now it's up to you to figure out what you're gonna design, right? Okay, update schematic close. Okay, so now you are looking at a nice figure which is better than 2.9 here and over here, and the match is better than 10, and then you have a droop. Okay, so there is a 10 dB here again, and there is a 9.1, so 0.9 dB droop is there. So you see, the whole purpose of this exercise is to tell you the trade-offs. Okay, and I haven't put this gain stage for a PA or a LNA. Okay, for a LNA I will bias it at a much lower current, and when I bias it at the lower current, my noises, which we talked about in the previous session, are going to be less, and this things is going to go down. Another way to bring down noise would be, I will just give you a very short this thing. Let's say if I have this inductance increased by 10 picohenry. Okay, so go to lump components. So source degeneration is also one of the way. Okay, so let's say that this is going to be 10 picohenry. So I have increased 34 picohenry to 44 picohenry, right? And say okay, hit simulate. So this has gone from 2.9 to 2.8, but the gain has also gone down. Okay, so let's put a tune on this one. So simulation tune. So I'm just showing you all the things which is going to affect you. So this is going to be L7. So let's say if I increase L7. Okay, so you will see that the noise figure is going to go down. So this is 15. Let's say make it 40. So noise figure is going to go down. You see here? Okay, but then you will have to match this again. Okay, so you'll have to match this. So I don't want to sacrifice this one. So you have to match this again. So which one is L4C4? L4C4 is over here. So okay, we are back in business. Okay, so I'll say update schematic close. So now this noise figure can be improved because it's a function of this, right? Now you would have to go ahead and create this by taking the via. So you take that via and you are going to spread them apart more so that there is more inductance added here and here, right? Or you make this thinner, this trace thinner, so that the source inductance can go up. So that way you can also control the noise figure, right? So I have told you a number of things. It's just not matching, also the stability, the bandwidth, the gain group, right? And also the noise figure. So this is a small exercise in small signal matching. Large signal matching is going to be a way different because there the idea is not the noise figure, rather the idea is the compression. So I would show you that you do not have to rely on load pull. You can do this if you know the impedances. So in the next session, probably I will show you how to do a large signal tune. So in this exercise, we have seen, whatever we could do with a small signal tune. So I'm going to stop here.